Hi, everybody. Welcome back. So this is going to be the final session of part one, chemical kinetics. Okay. So today we'll be discussing about the kinetics of nth order reaction, pseudo order reactions, and we'll be doing some problems. Okay. And that's how we are going to wind up the session. Okay, chalo. So without any further delay, note down the heading, any order reactions or kinetics of nth order reaction. Kinetics of nth order reaction. N. So what are we considering over here? We are going to consider that the order of the reaction is N. Okay. So you can use whatever equation that you're getting over here. We can put it for n is equal to 2, n is equal to 3, 4, 5, etc. Any value except 1, where n is not equal to 1. Okay, you cannot put whatever equation we are going to derive now. You cannot use it for first order reactions. Except first order reactions, you can use the equation for any other reaction. Now, our reaction would be A giving products. Comparing the theoretical and the experimental rate, we have been doing this for a while. So it's going to be changes in the concentration of A with respect to T, which is the theoretical rate, is equal to rate constant into concentration of the reactant to the power N, which is the experimental rate. Correct. Now I'll bring the A terms to one side and I'll take dt to the other, the minus sign to the other side. So it becomes minus dA by concentration of A to the power N is equal to K dt. I'll take the minus also to the other side. So it becomes like this. dA by A to the power N is equal to minus K dt. Now I can integrate. I'll integrate from t is equal to 0 to t. So when the time is initial time t is equal to 0, our concentration will be A naught and our final concentration will be A. Correct. Now we need to integrate this. We know that integral 1 by A to the power n dA is equal to integral A to the power minus n dA. This is how we write. So this was in the denominator A to the power n. When we take it to the numerator, it becomes A to the power minus n. Now those who are confident with the integration can do it on your own. So what is the formula of integration? It is A to the power minus n plus 1 divided by minus n plus 1 is what we are going to get. Now this is in the numerator, right? When I take it to the denominator, again the signs will change. Correct? The signs will change and it becomes 1 by 1 minus n, which is the constant, into 1 by A to the power minus n plus 1 it is. So when I take it to the denominator, it will become A to the power n minus 1. A to the power n minus 1. Okay, now I'll put these results over here. So I have a common constant 1 by 1 minus n into, after the integration, what I have is 1 by A to the power n minus 1. I need to put the limits equal to minus k and integral dt is t and I need to put the limits here as well. Okay. Now I'll take this 1 minus n to the other side. So on the left it is divided by 1 minus n. On the right it becomes into 1 minus n. And there is already a negative over here. Correct? So let's put the limits first. upper limit minus lower limit. So it is 1 by concentration of A to the power n minus 1 minus 1 by initial concentration to the power n minus 1 equal to upper limit minus lower limit is just T. And I took 1 minus n to the other side and there is a minus over here. Kt. Correct? Again, taking negative inside, this becomes 1 by concentration of A to the power n minus 1 minus 1 by initial concentration to the power n minus 1 is equal to n minus 1 Kt. That's it. Okay. So this is the equation for the kinetics of a nth order reaction. Nth order reaction. Correct. Now, if I have to write the equation for T half. So this is a common equation. Again, I repeat, you can use this equation to find the integrated rate equations for any order reactions except 1. You cannot use it for 1. Okay, let's put n is equal to 0. If you put n is equal to 0, you will get 1 by concentration of A to the power minus 1 minus 1 by initial concentration to the power minus 1 is equal to 0 minus 1 Kt. Okay, upon rearranging, this becomes concentration of A minus initial concentration is equal to minus Kt. Taking negative to the other side, it becomes initial concentration minus whatever is left is equal to Kt. This is already something that we have derived. You cannot use it for n is equal to 1. Why? Because 1 minus 1 is going to be equal to 0 and you will end up getting 1 minus 1 again 0 into Kt. So it's not going to be valid. You cannot use it for n is equal to 1. For that, you will have to learn. What was the equation? Ln of initial concentration by final concentration is equal to K. This was our equation. What if the value of n is equal to 2? So 2 minus 1 minus 1 by initial concentration to the power 2 minus 1 is equal to Kt. We derived this as well. Let's try n is equal to 3 as well. 1 by final concentration to the power 3 minus 1 is equal to 2. Minus 1 by initial concentration to the power 3 minus 1 is equal to 2. Equal to 3 minus 1, 2 Kt. Okay. So this is the general equation for the integrated rate equation for reactions which proceed with order n except 1. You cannot put the value of 1 over here. Okay. Now, using this equation, please calculate the general formula of T half as well. Calculate the general formula of T half as well. Okay, after plugging the values and rearranging, I'll write down the equation. T half for nth order reaction, okay, is equal to 1 by k n minus 1 into 2 to the power n minus 1 divided by initial concentration to the power n minus. This is the equation. for the T half of any order reaction. It will be nice if you are able to by heart this. It will be helpful. Important. Important. So just like the way we found the integrated rate equations, you can also find the T halves. Let's try. Let's find T half for n is equal to 0. It's going to be 1 by 0 minus 1 is minus 1. 2 to the power 0 minus 1 minus 1 divided by A naught to the power 0 minus 1. Correct. So this is going to be minus 1 by k into 2 to the power minus 1 is 1 by 2. 1 by 2 minus 1 is 0.5 minus 0.5 divided by A0 to the power minus 1. So minus into minus becomes plus. 0.5 can be written as 1 by 2 k. It's A0 to the power minus 1. When it comes to the numerator, it becomes A0. This is the T half of a zero order reaction which we have already derived. Correct? We cannot find the T half of n is equal to 1 over here. Not applicable. You will have to know that T half when n is equal to 1 is 0.693 by k. Okay. We can try it for n is equal to 2. Plug in the values. 1 by k into 2 minus 1 into 2 to the power 2 minus 1 minus 1 divided by A naught to the power 2 minus 1. Easy. Which is equal to 1 by A naught into k. Easy. T half when n is equal to 3. 1 by k into 3 minus 1 into 2 to the power 3 minus 1 is 2 minus 1 divided by A naught to the power 3 minus 1. 2 to the power 2 is 4. 4 minus 1 is 3. So it becomes 3 by 2k initial concentration to the power 2. Okay, so you can use this as well to find the equations for the T half of any order reactions except one. Now, a very important relation from here. If you compare T half and the initial concentration, if you compare the T half and the initial concentration, they are related inversely. How are they related? T half of any order reaction is inversely proportional to the initial concentration to the power n minus 1. Very important. We'll be doing problems today as well so that you have a better understanding. Just understand that they are inversely proportional. T half is inversely proportional to the initial concentration to the power n minus 1. Correct? So you can see here. If you put n is equal to 2, here it becomes 2 minus 1 A naught. If you put n is equal to 3, the denominator over here becomes 3 minus 1 A squared. Okay, so you have to know this relation that T half of any order reaction is inversely proportional to the initial concentration to the power n minus 1. Okay, so with that, we wind up the kinetics of nth order reaction. Next heading, pseudo order reactions. Please note down the heading. Pseudo order reactions. Very easy. Pseudo-order reactions means, we'll explain it with an example. Let's say that you are studying the ester hydrolysis. Okay, we'll explain it with an example. Ester hydrolysis. Any reference book that you take, this will be the first example that you have. So that is CH3COOC2H5. Consider an ester in the presence of water and any acid. Let's say it hydrolyzes. Please note it down. Okay. Hydrolysis occurs and this becomes CH3COOH plus C2H5OH. Okay. Now the rate of this reaction can be written in many forms. This can be written in many forms. So consider some situations. So case 1 is where this is an elementary process or this is an elementary reaction. So what do you mean by an elementary reaction? If it is given that a reaction is elementary, you can easily write the experimental rate. Correct? How do you write the experimental rate? Experimental rate is equal to rate constant into concentration of reactants raised to their stoichiometry. So this is going to be concentration of the ester into concentration of water into concentration of H plus. This is going to be the expression of the rate corresponding to the elementary reaction. Okay. Now consider that in this elementary reaction, the concentration of acid does not change. Or else you can say that H plus acts like a catalyst. Like a catalyst. So you might have heard about acid catalyzed reactions, base catalyzed reactions, etc. Okay, so if it is an acid catalyzed reaction, we do know that nothing happens to the catalyst. If you start with 10 units of catalyst, you will have 10 units of catalyst at the end as well. There won't be any change in the amount of catalyst. So if concentration of H plus is like a catalyst, meaning it is a constant, meaning it does not react, it just supports. I repeat, it does not react, it just supports the process. And at the end, whatever H plus was used is regenerated. So if you start with 10, it ends with 10 molecules. Okay, so H plus is a constant means that does not have any effect on the rate. So the rate is now K into concentration of the ester into concentration of water. Because concentration of H plus is a constant, it does not have any impact on the reaction. It is just a catalyst which provides a surface or an alternative pathway. That's all. We'll be learning about catalysis in detail. Okay. So if you can see, in the first case, our total order of the reaction was 1 plus 1 plus 1, 3. But when you gave certain conditions, assumptions, now it has been reduced to 2. Now this is a pseudo-order reaction. This is called pseudo second order reaction. It is pseudo. Pseudo means false. It's not actually 2. We have taken a particular assumption that H plus is constant and it has become 2. Okay, so it is a pseudo order reaction. Let's put one more condition. Like let's say the concentration of water is excess. Excess means let's say you have only 10 ml of your ester and the amount of water that you take is let's say 20 liters. So adding a 10 ml to 20 liters for a reaction to happen. What if this volume is not 20 and it is 19.9? Does it make any effect? No. What if it is 20.1 liter? Does it make any difference? No. Why? Because water is so excess that it does not make any effect on the rate. So much of water molecules are present that it does not have any effect. Even if you change the volume, the reaction will proceed because it is in excess. Okay. Now, so what will be our rate? It will be just rate constant into concentration of the ester alone. Because water has no role. It is present in excess. Even if you decrease or increase by a few ml, that's not going to impact the ester hydrolysis of just 10 ml of our sample. Now, what is the order? It has become 1 and it is a pseudo first order reaction. Pseudo first order reaction. Okay. So, pseudo order reactions are those reactions where the order of the reaction is found by taking into consideration of certain assumptions like case 2 and case 3. That's all. Okay. So you should know this concept. Let's do a question. Okay, note down the question. Question number. Okay. Question number 20. Question number 20 of chemical kinetics. Question number 20 of chemical kinetics. Note it down. The inversion of cane sugar proceeds with T half is equal to 500 minutes at pH is equal to 5 for any concentration of sugar. So there is an inversion of sugar taking place, which is the process. T half is given as 500 at a pH of 5. And they are saying that for any concentration of sugar. Very important statement. For any concentration of sugar, the T half remains 500. What does that mean? Okay. Think on that. Rest of the question. However, if pH is equal to 6, the T half changes to 50 minutes. The rate law expression for the inversion process can be written as okay. Option A, rate is equal to rate constant into concentration of sugar to the power 2, H plus to the power 0. B, rate is equal to rate constant into concentration of sugar to the power 1, H plus to the power 0. C, rate is equal to rate constant into concentration of sugar to the power 1, H plus to the power 1. D, rate is equal to rate constant into concentration of sugar to the power 0, H plus to the power 1. Okay, think on this. Read the question well. They have said that the inversion of the cane sugar proceeds with T half is equal to 500 at pH 5 for any concentration of sugar. Very important hint, which means T half is independent. It is independent on concentration of sugar. Correct? Now we know that which order reactions usually are independent on concentrations of the reactant. So what is the process over here? You have sugar, which is the reactant, reacts and it gives products, whatever it is. And it is given that the T half is independent on the concentration of sugar. We know that T half for a first order reaction is 0.693 by K, where it is independent on the concentration of the reactant. Correct? It is independent on the concentration of the reactant. Hence, the order of the reaction with respect to sugar is 1. How did you get that? Because T half is not changing with concentration. T half does not change with the concentration of the sugar, meaning it is a first order kinetics with respect to the sugar only. So now look among the options. Here the concentration of sugar is depending in a second order kinetic manner. So it's not option A. Here it is zero order, so it's not option D. So you can cancel two options. It's either B or C. Okay. Now let's see. It's given that at pH 5, T half is something. At pH 6, T half is something else. So how do we do that? For this, you have to know that pH is minus logarithm of H plus. Going back to our early school days. pH is minus logarithm of H plus. So there are two cases given, right? They have given that pH was initially how much? 5. pH was 5, meaning minus logarithm of H plus is equal to 5, meaning log of H plus is equal to minus 5. If I take antilog on both sides, this is going to be H plus is equal to 10 to the power 5. Correct? If you have log x is equal to y, how will you take the antilog? X is equal to 10 to the power y. Okay. Now, other cases, pH value is equal to 6. So, minus log H plus is going to be equal to 6. Meaning, taking negative to the other side, log H plus is equal to minus 6 or H plus is equal to 10 to the power minus 6. Now, let's compare what is given in the question. When pH is 5, meaning H plus concentration is 10 to the power 5, our T half was 500 minutes. And when the H plus concentration is 10 to the power minus 6, which is even smaller, correct? T half has become 50. This is what is given in the question, correct? At 5, it is 500. At 6, it is 50. Now see what has happened. What has happened? When Let's say that you increase it from minus 10 to the power minus 6 into 10 is equal to 10 to the power minus 5. Okay. So let's say from 10 to the power minus 6, you increased the concentration of H plus 10 times. Your T half also has increased 10 times. Correct? So T half is directly proportional to the concentration of H plus. Now, which order reaction has an equation where T half is directly proportional? We know that T half for a zero order reaction is A0 by 2K, where T half is directly proportional to the concentration of whatever reactant it is. Here also we are getting the same, which means it is a zero order kinetics with respect to H plus. Zero order kinetics with respect to H plus, it's option B. Very beautiful question. Mark it as important, please. Very nice question. So since T half is directly proportional to concentration of H plus, it follows zero order kinetics. It follows zero order kinetics. Okay. All right. Now we'll practice few questions and then we'll wind up. Okay. Very easy peasy questions. Let's try. Question number 21. A rate law for a reaction between A and B is given by rate is equal to K into concentration of A to the power N into concentration of B to the power N. On doubling the concentration of A and halving the concentration of B, the ratio of new rate to earlier rate will be. Very easy. Option A, 1 by 2 n plus n. Option B, n plus n. Option C, n minus n. Option D, 2 to the power n minus n. Very easy question. What is given? Rate is equal to rate constant into concentration of A to the power n, concentration of B to the power m is given. Correct. Now they are saying that they are changing. So upon changing, let's say that the new rate is R prime. So rate constant won't change. Concentration of A is doubled and concentration of B is made half. Correct? Now you have to find how are they related. So we need to take R prime is equal to K. I'll take 2 to the power n outside, A to the power n, and then I'll take 1 by 2 to the power m outside, B to the power m. Correct? Now we know that K 2 to the power n, K A to the power n and B to the power m. That is our equation for R. So I can write it as R prime is equal to 2 to the power n into 1 by 2 to the power m into R. So the new rate is 2 to the power n minus m times earlier rate. This is our answer, option D. Very easy question. Option D. Okay. Question number 22. The rate constant for 2N2O5 giving 4NO2 plus O2 is 3 into 10 to the power minus 5 per second. If the rate is 2.4 into 10 to the power minus 5 moles per liter per second, then concentration of N2O5 in moles per liter is, again, easy peasy question. So what is given? Rate constant. K is given. 3 into 10 to the power minus 5 per second. Rate is also given. R is equal to 2.4 into 10 to the power minus 5 moles per liter per second. We need to find the concentration. Now see, I had put this question over here to just remind you that even if in a reaction, they do not give you what the order is. Okay? So they have not given you what the order of the reaction is. It's just given that there is some rate constant and the order is this, sorry, and the value is 3 into 10 to the power minus 5 per second. That is enough. By just looking at the unit, we can understand that if you have just per second, the order is equal to 1. Correct? We have already learned this. Units of rate constants. If the order is just time inverse, it is a first order reaction. That's all. Now what do we want? Rate is equal to rate constant into concentration of A to the power 1. R is there. 2.4 into 10 to the power minus 5 moles per liter per second equal to rate constant is 3 into 10 to the power minus 5 per second into concentration. Our reactant is N2O5, so we'll write N2O5. That's all. Per second and per second gets cancelled. 10 to the power minus 5 and 10 to the power minus 5 gets cancelled. What you have remaining is 2.4 by 3. Concentration of N2O5 is 2.4 by 3, which is equal to 0.8, option D. What is the unit? 0.8 moles per liter, which means 0.8 molar. 0.8 molar. Okay. Question number 23. Predict the order of the reaction. Predict the order of the reaction where T half is half-life and A is the initial concentration of reactant. So the graph given is log T half here you have log A and you have a straight line. It is given that if you draw a line parallel to the x-axis, this angle is theta, which is equal to 45 degrees. This much is given. Very easy. This question was asked in GATE. Okay. You get a lot of questions from this relation, okay? T half is directly proportional to 1 by initial concentration to the power n minus 1. What is the relation which was given over here? Look at the graph and try to interpret. It is said that you have log T half and log A. So of course, we'll have to take the logs on both sides. Okay. Leave that. As you increase the concentration of log A, or as you increase the value of log A, log T half is also increasing. So it is a proportional relation. If A increases, log A will also increase. And as a result, log T half will also increase, correct? So we can say that from this graph, you can say that T half is proportional to, instead of A naught, they have given A. Anything can be given in the question paper, okay? We have learned it in terms of capital A naught. They have given just A. It's okay. Your concept should be clear. That's all. Okay. So T half might be proportional to A over here. Correct? Now, if I take, let's say I want to remove this proportionality sign, I'll write it as T half is equal to some constant into A. Now, if I take log on both sides, log of T half is equal to log of some constant into, sorry, not into, plus P, plus log A, correct. Log A into B is log A plus log B, correct. And that is a graph also, correct? You have y term log T half, you have x term log A, and you have got a theta value of 45, meaning the slope of this graph is going to be tan 45 degree, which is equal to 1. The slope over here is also 1. And it has got an intercept, which is going to be log constant value. Now, so this is sorted. Now we have to find a relation where T half is directly proportional to the concentration of the reactant. Okay. We have to find the order of the reaction where T half is directly proportional to the concentration of the reactant. And we know that. We already did a question. T half is equal to concentration of the reactant divided by 2K when the order of the reaction is 1. Sorry, when the order of the reaction is 0. Sorry. When the order of the reaction is 0. So the answer is, it is a 0 order reaction. Okay. See, children, you have to know that T half is directly proportional to the initial concentration for a 0 order reaction. It is independent of a concentration for a first order reaction. And it is inversely proportional to a 0 order reaction. So you can get graphs like this and questions can be asked. Okay. Now, from the same equation, from the same relation, let's do one more question. This was asked in CSIR. Question number 24. Question number 24. Half-life of a reaction A giving B is found to be undergoing a 9-fold increase as initial concentration is reduced to 1/3 at a given temperature. At a given temperature, the order of the reaction is. The order of the reaction is. Option A 0, option B 1, option C 2, option D 3. This was asked in CSIR. So they have asked a lot of questions from the relation, okay? So see, whenever you see a question where there is half-life and initial concentration, it should come to your mind that they are asking about this relation that we know. This is the first possibility that should come to your mind. Okay? T half is inversely proportional to the initial concentration to the power n minus 1. Now, what is given over here? They have said that there is some reaction and the T half increases 9 times, then the concentration is reduced 3 times. Okay, so first of all, I'll give you a relation by how this is done. This is actually a method. You need not learn it by a method and all. It's called a half-life method to find the order of the reaction. Half-life method. It's called half-life method because you use this equation to find the order. So the question is to find the order and you use this equation. It's called half-life method. That's all. Now I'll tell you how this is done. It's very easy. Let's say that T half is directly proportional to 1 by initial concentration to the power n minus 1. Now I need to relate it between two concentrations and two half-lives. Okay. For example, I have T half. I'll write 1 and 2, okay? T half 1 is proportional to 1 by A1, which is the initial concentration to the power n minus 1. And I have another half-life, T half 2, which is at a different concentration, A2, n minus 1. So if I have this and if I divide, let's say 1 by 2 or 2 by 1, whatever your wishes, I'm dividing 1 by 2. So what will happen? I will get T half 1 divided by T half 2. After rearranging this becomes A2 initial to the power n minus 1 divided by A1 initial to the power n minus 1. Correct? Or I can write it as T half 1 by T half 2 is equal to A2 naught divided by A1 naught the whole raised to n minus 1. This is one relation by which you can find the order of the reaction if you have two T halves and two initial concentrations given. Okay. Or you can elongate it further. You can find the log. You can take logs on both sides. Let's take logs on both sides. What happens? Log of T half 1 divided by T half 2 is equal to, this is log to the power, this is log A to the power B, which is B log A. Correct? I can expand this and I can write it as n minus 1 log of A2 naught divided by A1 naught. This can also be used as an equation. Correct? I can rearrange it further. I can rearrange it further. This is log A by B. I can write it as log A minus log B. Correct? So this is going to be log of t half 1 minus log of t half 2 is equal to n minus 1 into log of a2 naught minus log of a1 naught. Keeping n minus 1 on this side and taking the other one to the left, it becomes log of t half 1 minus log of t half 2 divided by log of a2 naught minus log of a1 naught. This is equal to n minus 1. If I want to find the order, I can take 1 to the other side as well. I just copy paste this equation. So if I take 1 to the side, this becomes this much plus 1 is equal to order of the reaction. I can find order of the reaction like this as well. Okay, so you need not mug up these equations. All you need to know is this. And then you can derive it in the example. That's fine. Okay, that's fine. So let's try and find the answer to this question. We'll use this relation and let's try. Okay. So what is given? In the question, it is given that the initial concentration, let's take it as A naught, okay, small a naught. This was the initial concentration first. This was our initial concentration. And then they're saying that after a while, this concentration was reduced by 3 times. Correct? This was reduced by 3 times. And what do they say? Initially, T half was, let's say, 1. After changing the concentration, T half changed to 9 times. It increased. That's all. Now we have to put that equation. What is our equation? T half 1 divided by T half 2 is equal to second initial concentration by the first initial concentration to the power n minus 1. T half 1, let's say, okay. So T half 1, we'll keep it like that. When you change the concentration, it becomes 9 times T half 1, correct? T half 2 is 9 times T half 1. So we'll write 9 times T half 1 is equal to, the second initial concentration is A01 by 3 divided by A01, the whole raised to n minus 1. Correct? So T half 1 gets cancelled. A01 gets cancelled. What do I have? 1 by 9 is equal to 1 by 3 to the power n minus 1. Very easy. For what value of n minus 1 will you get 1 by 9 on the left? Very easy. We know that 1 by 3, the whole square is equal to 1 by 9. Correct? So n minus 1 is equal to 2 or n is equal to 2 plus 1. Correct answer is order 3. Option D. Option D. Okay. So there are many methods in which you can find the order of the reaction. Here, the order of the reaction is found with half-life. In the earlier question, we found it from a graph. Okay. In the earlier question, we found it from a graph. You can also find the equation from the rates as well. This was asked in, again, CSIR. I'll give the explanation. We'll write it as a question. Okay. Question number 25. Question number 25. Important. This was asked in CSIR June 2016. Let me see if I have the question. Just a second. Okay, yeah, I have. So the question is, the rates of a reaction are the rates of a reaction are R1 and R2 at concentrations C1 and C2 of a reactant respectively. The order of reaction N with respect to the reactant is option A, N is equal to log R1 minus log R2 divided by log C1 minus log C2. Option B, N is equal to log C1 minus log C2 divided by log R1 minus log R2. Option C, N is equal to log C1 minus log R1 divided by log C2 minus log R2. Option D, N is equal to log C2 minus log R2 divided by log C1 minus log R1. Okay. Very easy, very, very easy. Options are all alike. So we have to mark the answer properly. Okay. Very easy. See, they are asking the relation between two rates and two concentrations. That's all. We know that R1 is going to be equal to rate constant into concentration to the power n, where n is the order. Correct? And let's say at a different concentration, the order of the reaction to won't change. The rate is becoming R. So that's it. We have 1, we have 2. We have to divide 1 by 2. So what will we get? R1 by R2 is equal to C1 by C2, the whole raised to n. So there is no option like that. We have to take logs. You can see all the options. They have log in it. So we have to take logs on both sides. So let's take logs on both sides. Log of R1 by R2 equal to log of C1 by C2 to the power n. Correct? Now expand and bring this n to the front. Log of a to the power b is b log a. Correct? So this becomes log of R1 minus log of R2 is equal to n log of C1 minus log of C2. So n is equal to log of R1 minus log of R2 divided by log of C1 minus log of C2. So if we look at the option, it's going to be R1 minus R2 by C1 minus C2, option A. Option A. Once you know the relation, and if you're confident with your basic mathematics, you can do this very easily. Okay? So this method of finding the order using rates and concentration is actually called the Van 't Hoff method. Van 't Hoff method. You need not learn the method. I'm just explaining the terms behind that. That's all. Okay. Last question. This was asked in again CSIR to find the order only. Question number 26. Question number 26. Okay. Consider the reaction between NO and H2 with following data. With following data. So case 1, the pressure of H2 is constant. And they have given the data for NO and the disappearance of NO with time. Okay. So it is 359, 300, 152. We have already done a similar problem. The rates are 1.5, 1.04, 0.25. Second case, the pressure of NO is kept constant and the data for H2 is given as 289, 205, and 147. Changes in concentration of hydrogen with time is also given as 1.60, 1.10, and 0.79. Question is, find the order with respect to H2 and NO. Find the order of the reaction with respect to NO and H2. Please pause the video and try. Please pause the video and try. Okay. So over here, it's very easy. You can just find the changes of the concentration and changes of the rate to find the order of the reaction. Okay, so here, if I say H2 is considered to be a constant and they have given, instead of concentrations, they have given pressures. Okay, so this is in mmHg. This one is also in mmHg. They have given pressures because the components are gaseous. And this was asked in CSIR net. They had 2013. Okay. So how can we approach this question? So it depends on how you observe the question. So there are many ways. You can choose your way, but I'll be explaining the easiest one. Okay. So if I look at the data, when H2 is kept constant and I look at the pressures of NO, from 152, if I increase it to 300. Now let's say that I approximate it to 150. Okay. Approximate. So 150 to 300, approximately the pressure is being increased by 2 times. What is happening to the rate? From 0.25, it's becoming 1.04. I'll approximate it as 1. So when I increase the concentration, when I increase the pressure by 2 times, my rate is increasing 4 times. Correct? Increasing the concentration of NO by 2 times is increasing the rate by 4 times. And increasing the rate by 4 times means the order with respect to NO is equal to 2. Correct? Because 2 to the power 2 is equal to 4. So N is equal to 2. Similarly, choose the values among which you can relate. Choose them. For example, if I choose this as 0.8 and let's say this is 1.6. So I can approximate almost. Okay, because in 2013 and all, you didn't have calculators, but now you have calculators. So you can do it in a much better and efficient way. But in olden days, we used to approximate a bit. And then we used to do the problems, okay? So now calculator is enabled, so you don't get such easy questions and all. But then to solidify a concept, it is very important to do previous year questions, correct? So it's very easy. We can relate these two, let's say 147 and 289. How are they related? 147 into 2, 147 plus 147 is actually 14, 19, 294 it is. It is 289, a difference of 5, that's fine. So if I say that my concentration of H2, keeping NO constant, is increasing 2 times, what is happening to my rate? My rate is also increasing 2 times. So whatever change I have brought in my concentration, that itself is the change in my rate. So 2 to the power 1 is equal to 2. So what is the order? Easy. Order with respect to H2 is equal to 1. So order with respect to NO is 2. Order with respect to H2 is 1. And the total order is equal to 3. Okay? All right. So that's it. We'll stop over here. All right, we'll continue in the next session. Now, you'll be receiving an assignment based on all these 7 lectures that you have heard. And also, I'll be putting maybe one more video on, again, problems. A bit more trickier problems so that you can have a better practice. Okay? All right, so that's all for today. Thank you, see you, and happy learning.